Unit 5. Way back to Unit 5. Ladies and gentlemen, today I will be walking us through the basics of Unit 5, and we're going to start with right triangles, baby. And actually, Unit 5 is all about right triangles. And in this particular example, we're doing Pythagorean theorem problems. Alrighty? If you don't remember, don't worry. The Pythagorean theorem states that for any right triangle, the square of one side plus the square of the other leg, I should say leg, the square of one leg plus the square of the other leg is equal to the hypotenuse squared. So, guys, whenever you're using the Pythagorean theorem, remember, C has got to be that longest side hypotenuse. A and B don't matter that much. You can trade those out for whichever you want. But C has to be that longest side. Okay? For us, we're going to start out here. Let me zoom in a little bit with just some examples. And guys, I'm just going to do a full reteach of the basics. I'm not going to prove the Pythagorean theorem again, but we're going to use it. Okay? We're going to use it as we can. Ziggy's feeling strange today. If you don't know, Ziggy is the name of the camera. I'm not kidding. That is not a joke. Whoever named this camera before me named it that. Anyways, so let's try this out. On this problem, to locate the hypotenuse, we look at the 90-degree angle. Across from that 90-degree angle is the biggest side of the triangle. This is because of the triangle inequality. Alrighty? These two angles are definitely smaller than 90, so the one across from 90 gets the most length. So this side must be C. And then here, since we know two sides, we can use the Pythagorean theorem to solve for the third. Here's me writing out the Pythagorean theorem. And so on one side, we're going to say A can be X. So we plug that in. On the other side, here's our B. That could be 13.1 squared equals. And this guy's going to equal to C squared, which of course is 20.5 squared. So now we live with this out. We just solve for X. Now, if you don't know how to solve for X, I would say make it easier on yourself. If you can't see what number it is immediately, make it easier on yourself. So for example, what would be easier than this is if I actually calculated these out in the calculator. I don't know what 13.1 squared is. Let me ask the good old calculator what that is. So 13.1 squared has got to be 171.61. So I'm going to fill that in first. And then on this other one, we have 20.5. That's also squared. And we get 420.25. Look at that. Excellent. And here, to solve for x squared, I need to get x squared alone. So right now, he's being hindered because he has this guy on the left-hand side. So to get him on the other side, let's subtract 171.61 from both sides. Here's 420. And what I'm going to do here is I'm just going to arrow up and hit enter to grab these other two numbers so that I don't have to type them again. And I get 248.64. Very nice. And so if x times itself is 248.64, what does x have to be? To find out, we'll come over here and square root both sides of this expression. Because the opposite of being squared is square rooted. And we'll take the square root of 248.64, and we get 15.7683228, which is approximately... Ready? Here, our problem has asked us to round to the nearest tenth. So for this particular problem, we're going to approximate this to 15.77. Ready? Since this 76 rounds up, oh my gosh, I'm crazy. Look, I just rounded to the hundredths place. Look at that. The tenths place is this guy. So of course, it actually still rounds up. So this actually approximates to 15.8. And there's no units in our answer, so we'll just write units and box it in. Okay, so that is a long-winded version of the Pythagorean theorem. You basically write it out, plug in what you know, solve for the remaining side. I'm going to do the exact same thing for number 2, but a little bit faster. Remember that this test we're studying for is a multiple choice test. So you'll be able to test out different answers if you're concerned with one of your answers. So anyways, I'm going to write it out quickly. If I was doing this fast, I would label, I know this is A and B because they're both touching the 90 degree. And then across from the 90 degree is C. So this problem's setup is 24 squared plus 19 squared is equal to x squared. And here to solve for x, I'm going to put in what is 24 squared plus 19 squared. Oops, I need to do that. What is 24 squared plus 19 squared? It's 937. So on the left-hand side here, I'm going to leave a 937 is equal to x squared. And what's the opposite of squaring? It's square rooting. So we're going to square root both sides. And so we see that x is approximately, if I take the square root of 937, I get 30.61. Look at that, which rounds to 30.6. Since this one, let me use my pen here. Since this one is less than 5, we're going to round down to 6. So it stays 30.6. Ladies and gentlemen, there are no units, so I'm just going to write U for units. That is our final answer. Alrighty? So look, on this side, there was some algebra to do. I went in detail about how this works. And then on this side, I just kind of showed you, like, look, if you know what you're doing, it's pretty fast. And remember, the formula sheet does have this. So just to make a note up here, the Pythagorean theorem is on the formula sheet. So you do not need to memorize it necessarily, but knowing how to use it is equivalent to memorizing it, in my opinion. Okay, for the next one, for these guys down here, notice it's a little bit different. We want to determine if these three side lengths can form a triangle. And if they can, we're going to determine if that triangle is acute, right, or obtuse. So let's see here. To do this, we must first make sure our triangle is even a triangle. Alrighty? Imagine if I just reached into a bucket and pulled out 3 random sticks, there's no guarantee that they could make a triangle, right? If I had 2 extremely short sticks and one that was longer than both of them combined, if I try to make a triangle here by connecting the edges, right? These guys are not long enough to reach each other. So in this case, a triangle is not possible, you could say. Alright? So it's not guaranteed that these even make a triangle. So what I'm saying is, to test that out, let's see if the longest stick is too long, just like in our example. To do this, you add 4 and 8. Alrighty? 4 plus 8 is 12. Since 12 is more than 9, we're good. We have enough. A and B are enough to make C as a triangle. Alrighty? And so now, we need to know if it's acute, right, or obtuse. Okay, well, we have a theorem that only works on right triangles. So let's try that on it. If we try the Pythagorean theorem here, 4 squared plus 8 squared, like if we just see if it works, what is 4 squared plus 8 squared? That's 80, right? So on this side, it's 80. And I'm going to write equals, but I don't know. I'm writing a question mark here to show that I'm not sure if they're equal or not. On the other side, we have 9 squared, which is 81. Interesting. They're close. But is 80 equal to 81? No. All right, obviously. In fact, in this particular case, a squared and b squared are less than 81. So in this case, you would say 80 is less than 81. Alrighty? Now imagine if I had done this problem and I got exactly 81, then I would know it has to be a right triangle because the Pythagorean theorem only works on right triangles. So if I got 81 equals 81, I would know it's a right triangle, but I didn't. In fact, alrighty? Imagine a right triangle, perfectly right. In fact, look, the hypotenuse here, c squared I should say, is more than the other two sides. It's more. This piece is wider Alrighty? So hopefully you can see what I'm going for here. If the C gets bigger, then doesn't that make this triangle obtuse, right? It used to be 90. Now 81 is too big, so it's become obtuse. In other words, we can write obtuse here safely. This is called the converse of the Pythagorean theorem. Since we started with all the numbers and talked about a triangle, that's the opposite of what we did before, right? That's the converse of starting with a triangle and then finding the numbers. Alrighty? Anyways. So for example, we can keep going here. And it does not have to take this long, it does not have to be this involved, right? All we have to do here is make sure it makes a triangle. 6 plus 17 is definitely more than 18. So it works. We have enough to make 18. So this is a triangle. Alrighty? Is it a right triangle? All we have to do is take 6 squared plus 17 squared. On this side, we get 325. And then on the other side, let's take 18 squared. On the other side, we get 324. So in fact, no, this side is bigger. They're not equal, so it can't be a right triangle. And look, this is the opposite case that we had before. Earlier, the hypotenuse got bigger, so the triangle became obtuse. Now, the hypotenuse gets smaller. And so, our triangle becomes acute, less than 90. Excellent. Alrighty, let's keep going here for the next one. We can do the same business here. First of all, can we make a triangle? Absolutely. 24 plus 45 is obviously more than 51. So that is enough to make a triangle. And then here, 24 squared plus 45 squared. We get 2601 on the left-hand side. And maybe I'll just write out this is a squared plus b squared. Alrighty, and then over here, we want to know, on the other side, what is 51 squared? It's 2601. So look at this. So wait, you're telling me the Pythagorean theorem worked. 24 squared plus 45 squared really is equal to 51 squared. In other words, a squared plus b squared is equal to c squared. The Pythagorean theorem holds, you would say in mathematics. You often say this theorem holds when it's true. And so this means this must be a right triangle. It is exactly equal. And just so you guys know, it does have to be exactly equal. If you got 2601.1, even though that triangle is really close to being right, it's not quite. It's actually acute. Alrighty? For our last one here, same business. 15 plus 17 is actually equal to 34. Look at this. 15 plus 17. I'm crazy. It's less than my fault, bro. It's actually less than 34. It's only 32. Alrighty? So actually, this is one of these scenarios. 34 is too big to connect 15 and 17. In other words, 15 plus 17 is too short to make 34, and so this cannot make a triangle. And so our answer here is not necessarily, it says if they can, determine the size of a triangle if they can, then the triangle is obtuse. So if we're reading the directions here, it says to determine if it's a triangle. We would just write that here it is not a triangle. Alrighty? And if you're curious, this is because of what's called the triangle inequality. Alrighty. That we learned back in Unit 3, I think. Unit 3 or 4. Very cool. By the triangle inequality. So, keep that in mind. Sometimes they're not triangles. They look like this. Sometimes they're acute. They're thin. Sometimes they're obtuse. They're fat. Sometimes they're right. They're perfect. They're like perfectly right. Okay, anyways. Let's keep going here. We also have the next target, which is BC. So, BC is down here at the bottom for me. It says to identify pairs of similar triangles formed when an altitude is drawn to the hypotenuse of a right triangle and use this to help solve problems. So basically, we're going to find the geometric mean here. Now this one I want to say, the geometric mean is not on the formula sheet. So here, if you're working on this at home, make sure you know how to find the geometric mean of two numbers. Alrighty? Well, Mr. Shirley, what is the geometric mean? Good question. First, I ask you, what does a mean? Okay? A mean is like an average, a middle, somewhere in the middle. Okay? If you were to take the average of two numbers, like 12 and 31, and just to be safe here, this is the arithmetic mean. It's often called the arithmetic mean. What you learned in middle school is that 12 plus 31, you can add up these numbers and then divide by how many there are to get the middle, which is 21.5. Okay? So this is the middle if you were adding. The geometric mean is like the middle if you were multiplying. Alrighty? In other words, if I take 21.5 minus 12, 21.5 is 9.5 away from 12, but it's also 9.5 away from 31. If you subtract, they're the same distance away. So, it's in the middle. The geometric mean does the same thing, but with multiplication. And to find it, it's very simple. The geometric mean x is given by the square root of the small number times the big number. Alrighty? And so, for example, we'll take the square root of 12 times 31. It's just very similar. Here we have two numbers, and we take the square root, which is the second power, right? Or the half fractional power, truly. And we get about 19.28730,152, which is a lot. Okay? To show you what I mean here, this is approximately, and it should be exactly equal, but we're going to write approximately 19.3 here. Alrighty? Okay? If you were to use this whole number, it turns out that 31 divided by this number is 1.60. But also, so let's see here. 31 divided by the geometric mean is this number. And the geometric mean, divided by 12 is also this number. So the geometric mean is like the middle if you're multiplying. If you multiply 12 by this number, you get this. If you multiply that number, the geometric mean, by this, that same number, you get 31. Okay? So this is the multiplicative middle, you could say, the multiplicative middle of what's going on here. Anyways, and so for number 8, same business. Obviously, you don't have to go through this every time. If you know the geometric mean is just the square root of 4 times 9. 9 times 4 is 36. The square root of 36 is 6. Ready? And guys, I will say typically geometric mean is positive. Technically, there is a plus or minus here, but the geometric mean for us is positive. It wouldn't make sense to say that, at least in geometry for now, that negative 6 is a possible geometric mean, even though it technically is. Alrighty, very cool. Let's keep going here. Why do we care about the geometric mean? It actually solves more triangles for us. More triangles. Alrighty? To use a geometric mean on a triangle, it's very simple. Show you guys what I mean here. The goal is to find the number that's in the middle multiplicatively, which is what the geometric mean does. So, for example, if I want the inside piece, this inside piece is actually the geometric mean of the left and the right. These legs here. Alrighty? And guys, this comes from similar triangles. We'll show another example where I do similar triangles in a second. Okay? For the inside, it's equal to the square root of the leg times the leg. Alrighty? Left times the right. If you're a formula person. So here in this case, x is equal to 8. The square root of 8 times 10, which is approximately, and let's see here, I don't know why I put that in the calculator. That's insane. You get 8.94. Now, we went around to the nearest tenth, so this is 8.9. Okay, there's no units given, so we're not going to write our units. That's fine, whatever. And we'll keep going. For this one, it's the same thing. If you're a formula person, if you're memorizing, then it is the case that this value on the outside is equal to the geometric mean of the closest piece and also the total. So in this case, I would say the outside is equal to, so the inside's this, the outside is the closest, the geometric mean of the closest times the whole part. Alrighty? So if this had been split into two sections, it'd be up to us to add those together for the whole. And for example, we can keep going here by saying, well, obviously, 6 is the outside, and that's equal to the square root of the closest, which is x, times the whole, which we say here is 15. Okay, and now since x is inside the radical, I'm actually going to square both sides of the expression. Alrighty? If this thing on the inside has the square root to 6, that's the same as the inside part being equal to 36. Okay? And then we're going to take 36 divided by 15 to get 2.4. And that's our value for x. Very nice. Okay. And let's see. The next thing I would like to do is try similar triangles for these. Guys, if you want these formulas to work every time, as long as you're careful, like on this one, where you plug in x where it's actually supposed to go, just throw it in there randomly. Alrighty? For these guys, it may be easier for you, if you're not a memory person, to simply create similar triangles and do a proportion. Amazing. Do a proportion. Okay? So, for example, let me show you what I mean. Maybe easier if you have colors for this. You don't need them, though. I'm going to use orange and red for my colors. Alrighty? And all I'm going to do is draw out my triangles. Here's one here. So here's my red triangle. And I'm just going to copy down like it looks. This angle's 90, right? This one right here. The bottom is x. The top side is 4. And I actually don't know this side, so I'm going to leave it blank. Okay? And then in orange, my other color, I'm going to draw on this piece. Alrighty? So this triangle is the smallest. This is like the medium triangle. If its right angle is here, and now look, I'm actually turning this triangle this way, 90 degrees this way, so that I can write down its processes. And I can actually read that. It doesn't come up great on the camera, so, well, actually, I guess it is okay. 6 is going to be the longer edge, so that's this side, and then 4 will be the shorter edge. Alrighty? So look, I use the same 4 for this one and for this one. Alrighty? And also you could do, in black here, I'm going to do the biggest triangle, this one. Okay? Now, if its right angle goes in the corner, then I don't know the left side or the right side. They're both blank. But the hypotenuse is x and 6. So this is x plus 6. Okay. So now to set up my proportion, I'm looking for specific objects that have something in common. To make a proportion, I need to have some things in common. So here, for example, do you guys see that on these two triangles? I know the right-hand side and the bottom. Alrighty? So this is an indication that I could make a proportion. Alrighty? And so what I'll do here is, I could say, well, since these guys are on the same triangle, 4 goes with x. Alrighty? The ratio from 4 to x must be the same as the ratio from 6 to 4. Very nice. And so to solve my proportion, you can always, always, always cross multiply and divide. Ready? I'm going to take cross multiplication here. Don't call it butterfly method. And in the next step, I have 6 times x, that's 6x equals. And then here, 4 times 4, that's actually 16. And so then I'll divide both sides by 6 here to get x must be 2.6 repeating, or 2 2/3. I'm going to write 2 2/3 just for accuracy's sake and box it in. Okay. I hope that I have not confused you with my drawings. I'm going to try it one more time. Remember, these are 2 different worlds. These are 2 different approaches to the problem. The similar triangle method, is how you derive the geometric mean. So both of them do the same thing. If this one's easier for you because it's faster and less steps, then do this one. If this one's easier for you because you can actually see what's happening in the problem, then do this one. Alrighty? No one's making you do anything a certain way, please. And so we'll continue. I would like to show number 12, then I'm going to take a quick break because I'm losing my voice, and we're already 30 minutes in, then I'm going to do 5D. Alrighty? So, for number 12, it's very similar. I'm going to draw my same picture. I'm not going to use colors this time to see if we can do it on our own. Alrighty? Try and sort these triangles out on your own really quick before I do it. Take this moment. Pause the video. Pause the video, Chief. Pause the video. Now. Alrighty? Just kidding. Hopefully you're back from the... Wow, look, this is like when you open your eyes. Wow. Oh my gosh, you're back from pausing the video. I'm so glad that you actually paused the video like you were supposed to and attempted this on your own so that you could learn with your full potential instead of just listening to a guy on a screen. Incredible. Right, so anyways, just kidding. If you don't want to try the problems, you don't have to. I'm just being funny. So anyways, here we go for number 12. I'm going to draw my triangles first. I have more room on this side over here, so I'm going to draw them over here. It doesn't really matter. I'm going to start with the littlest one. He's my favorite. Okay, the 90 degree goes here. And if I'm turning that this way, you guys see here's my 90. It's facing towards x, so I'm going to call this side x. And then the side next to x on the bottom, it's got to be 9. Okay, and now for my medium triangle. In my medium triangle, so here's the small, here's the medium. In the medium triangle, I don't know this side, I don't know this side, but I do know the long leg, righty? Which has got to be 12, okay? And then finally, we also have the biggest triangle, who's actually already oriented correctly. The biggest one, I know the bottom of the biggest one is x, and then look at this. The hypotenuse of the large one is actually 2 values put together. It's 9 plus 12, which is 21. How cool. So, to set up my proportion, I need 2 triangles that have 2 things in common. So, like, look at this example we did earlier. These 2 triangles worked because I knew 2 of these things that they had in common. In this scenario, I'm going to choose these triangles to relate. Since I see that my hypotenuse is known on both, and I guess it should not say known, it's represented with something, right? And then also the bottom leg is represented by something. So to make my fraction, I'm going to relate these guys because they're on the same triangle. So I'm going to say the ratio between x and 9 must be the same as, and look, I'm going from x to 9. So on this one, I'm also going from 21 to x, right? That has to be the same as the ratio from 21 to x. How fascinating. And so to solve this problem, I've actually, I've doomed myself. I've run out of room. But I'm going to come up here to finish it off. If you cross multiply here, we get something really cool. 21 times 9. Now that is 189, I believe. Let's see if I'm right. I don't trust myself. Okay, nice. 189. So on the left-hand side here, 21 times 9, that's 189. And on the right-hand side, I get x times x, which is actually x squared. Wow, I know, groundbreaking. Okay, so if we take, now to solve for x, we're going to take the square root of both sides. Alrighty. Hopefully this looks like the geometric mean to you. It should. Ready? So I'm going to take the square root of 189, 13.74, or 13.75. For us, round to the 10th, so that's 13.7. And we're done. How nice, how beautiful. Guys, I will see you in the next one for trigonometry.